We learn in our classes that temperature is a measurement of the average kinetic energy of the molecules surrounding us. When we say that it's warm outside, we're just measuring the larger and more frequent collisions of the molecules with our skin. But are we measuring the temperature at the level of our individual cells, or is it some larger collective effect? I mean, if I were to take the tip of a thermometer and shrink it smaller and smaller and smaller down to the size of an individual cell, would it continue to measure the same warm 30-degree temperature? Clearly, if the tip of the thermometer is the size of an individual atomic molecule, then it can't possibly measure the average collisions or the kinetic energy of the surrounding air molecules. So then, how big exactly does the measurement tip of the thermometer need to be for us to have a well-defined temperature? And how big does a control volume need to be for that volume to measure a well-defined density, pressure, and energy? Today, we will introduce the concept of the continuum. Suppose that I want to describe the properties of the gas molecules inside this room, like its temperature, density, viscosity, and thermal conductivity. After all, we often write down the equations for the law of conservation of mass, momentum, and energy, which involve variables like temperature, density, and velocity. So let's draw a box with edge length L and describe the properties of the molecules inside that box. And what we'll do next is to freeze the molecules to plot the density of the molecules inside this box as a function of the edge length L. The density of the molecules inside this box is defined as the total number of molecules inside this box, N, divided by the volume of the box, L cubed. At zero volume, there's going to be no molecules inside this box. But as we make the box larger and larger, we're going to pick up some molecules that enter this box. And molecules are going to enter and leave, so the number of molecules inside this box will fluctuate wildly, causing the density to fluctuate. And because the density is sensitive to inclusion of a single molecule entering and leaving, the density will fluctuate wildly. Eventually, we arrive at some steady value where we have very little fluctuations in the density. Now, at this stage, the box is so large that the density has stabilized to a steady value, a well-defined density. The crossover length between the large fluctuating atomic length scales to the left of this value L star and to the right of it is what is defined as the continuum length scale L star, as denoted here. Above this length scale, material properties inside this box are at a continuum scale. And with the continuum hypothesis, we are making the assumption that above this length scale, all material properties like the density, viscosity, thermal conductivity, as well as variables like the pressure, velocity, and temperature can be defined at a mathematical point. Therefore, the thermometer tip needs to be at least L star big to measure a reliable, well-defined temperature. In many applications of science and engineering, we are concerned with fluid motions or heat transfer in pipes, airfoils, bodies that are large compared to the molecular lengths within the system. So it's really important to know what this length is so that we know how to describe the properties at the continuum scale. Let's measure the distance between the individual molecules inside this room to figure out what this L star might be. Let's pick those two molecules. For a gas, the collisions between the individual molecules give rise to properties like the temperature, thermal conductivity, viscosity, etc. So let's try to calculate the average distance between the molecular collisions denoted by a length lambda. As a single gas molecule translates, it will carve out the path of a cylinder with the radius of the molecule r. The volume of the cylinder that the molecule carves out is given by just like that. And the density of the gas molecules in this room is given by it is simply the number of molecules inside this box divided by the length L cubed. So the density, this quantity right here, times the volume of the cylinder gives us the total number of molecules inside the cylinder. Since we are calculating the average distance between individual collisions, we only want a single other molecule inside this space. In other words, we want the product of these two quantities to equal 1. We can now solve for the average distance between the molecules by solving for this quantity lambda. This quantity is called the mean free path of the molecules. Here, we're just doing a very simple scaling argument to figure out the average distance between the molecules inside this room, inside your room. This is the solution we would get if we assume that our reference molecule is translating, but all other molecules inside your room is fixed. If one repeats the same calculation with all of the molecules translating, the mean free path is reduced by an order 1 factor. Square root of 2. Since we are doing order of magnitude estimates, let's not worry about this factor of square root of 2 at the moment. It's more of a technical detail. By using the ideal gas law, we can estimate the average density of molecules inside the room. At this stage, we now have everything we need to estimate the average distance between the molecules inside this room. A nitrogen molecule is about an angstrom in size, the pressure is 1 atmosphere, and the temperature is a comfortable 25 C. Okay. With these values, we can calculate the mean free path directly, which gives us a value of 1 micron. Just plugging in the values gives us about a micron. So the average distance between molecular collisions in this room, in your room, is about 1 micron, 10 to the minus 6 meters. Therefore, a molecule is traveling 10 to the 4 body distances before colliding into another neighbor. To use an analogy, that would be like a human, which is about a meter big, traveling 10 to the 4 meters. So 10 kilometers or 6 miles before colliding into another individual. If you're introverted, that would be an amazing world, and you would actually prefer that world. But that's what the gas molecules are doing. And it's remarkable to me that you can actually calculate this quantity with just a couple of lines of geometry and algebra. And let me ask you a question. Does this micron seem like a big number to you or a small number? When I actually first made this calculation in a class that I was taking, I felt like a micron seemed very large, because we can see a 1 micron object under a common benchtop microscope. For example, this is a image of a bacterial colony that I took using our lab's microscope. And you can see individual bacteria by the rod-shaped particles wiggling around and jiggling around inside this fluid. They're each about a half a micron in diameter and a couple of microns in length. So what this means is that a gas molecule in your room right now is traveling the distance of about a single bacterium, which we can see under a common microscope. And so that's why I felt like a micron seemed like a very large distance. And I used to think that a property of a molecular fluid or molecular system should be at continuum also on an atomic or molecular scale. But it turns out that a continuum property requires a much larger, 10 to the 4 particle size larger distances for us to have a well-defined temperature, density, and pressure. We now know how much a gas molecule has to travel between individual collisions, but what about the time scale? How frequently are these collisions taking place in your room? The time is simply the distance that a gas molecule travels divided by its velocity. And we can obtain the average velocity of the molecules by using the equipartition theorem. So we know the temperature, we know Boltzmann's constant, and we know the mass of a nitrogen molecule inside this room. And it turns out that the average velocity of a nitrogen molecule at standard temperature and pressures is about 500 meters per second. 500 meters per second. So a molecule is traveling a kilometer every 2 seconds. What this means is that an individual collision can be calculated directly. And when you make this calculation and convert the units, what you get is a nanosecond, 10 to the minus 9 seconds. This calculation is just so remarkable and mind-boggling to think about that inside this room, there are gas molecules whizzing around, going crazy inside your room right now. These molecules are whizzing around at 500 meters per second, traveling for a micron, and colliding into each other every nanosecond. So crazy things are happening in the world around us while we live out a boring life. Crazy things. And what's even more remarkable and exciting to me is that we can make all of these order of magnitude approximations of these molecular systems by just a couple of lines of geometry and algebra. It's so remarkable. And now we can return to our original question of, when are we at continuum? What is this length scale L star? How big does the tip of the thermometer need to be to measure a well-defined temperature? Well, we need to be at lengths much bigger than the mean free path of the molecules, lambda. So that means we need to be at least as big as a micron, usually much bigger than that. Exactly how much larger depends on your specific application, but as a general rule of thumb, even 10 times larger than the mean free path is a sufficient length scale for a system to be on a continuum scale for a gas. So even 10 micron scale, you can say safely that these molecules, you are sampling a continuum property.